Hello, everyone. Welcome to this week's ISyE seminar. We have with us Professor Shiqian Ma, who is an associate professor in the Department of Mathematics at the University of California, Davis. Professor Ma's main research areas are optimization and machine learning. He got his PhD in IEOR from Columbia University in 2011. And perhaps some of you have met him while he was an NSF postdoctoral fellow in the Institute of Mathematics and its application at University of Minnesota. Right? This was back in 2011, 2012. Before joining the University of California at Davis, he was an assistant professor in the Department of Systems Engineering and Engineering Management at Chinese University of Hong Kong. And he has served as the area chair for the International Conference on Machine Learning in 2021 and 2022, and currently serves on the editorial board of the Journal of Scientific Computing. So very happy that he has accepted our invitation, and I look forward to his talk, where he's going to talk to us about Riemannian optimization for projection robust optimal transport. So Professor Ma, whenever you are ready.
Okay, thank you very much. Thank you, Chris, for the very nice introduction. I want to thank you for the invitation. It's really my great pleasure to be here. It's very nice to come back to Minnesota, although virtually. So I'm very happy to meet many old friends and also some new friends. Yeah, great pleasure to be here. So today I will talk about Riemannian optimization for projection robust optimal transport. So this is based on joint works with my current students, Hui Huang, and also my colleague Yifeng Lai at UC Davis. So we wrote two papers on this topic, and both papers were published in SML last year. Okay, so this is the outline of my talk. In the first part, I will give a brief introduction about the projection robust optimal transport problem, or equivalently, the projection robust Wasserstein distance problem. So basically, the optimal transport problem finds many important applications in machine learning and deep learning. So for example, the most important application is the generative adversarial network problem. Basically, this problem is now drawing a lot of attention, but one potential issue about optimal transport is the curse of dimensionality. So there are a lot of techniques have been proposed to try to mitigate the curse of dimensionality. One recently proposed model is called the projection robust optimal transport problem. And this problem can be formulated as a minimax problem over a Stifel manifold. And so numerically, it is very challenging. So for this problem, we proposed a new algorithm. It is called the Riemannian block coordinate descent method. So Riemannian BCD method. And we analyzed the convergence and also the complexity of this algorithm. And compared with some existing method, we found that our method is much better, both theoretically and numerically. So in the last part, I will propose a new model, which is called the projection robust Wasserstein barycenter. So this new model can compute the mean of a set of probability distributions. And this problem is also very closely related to the projection robust optimal transport problem. Okay, so first let me introduce the optimal transport problem. This optimal transport problem is originated from Monge in 1781. Basically, we want to move one pair of sand to another pair, and we want to minimize the total cost or the total distance. So for example, here, this red part, this is one pair of sand, and we want to move this pair of sand to the blue part. And the red parts and the blue parts, they have the same volume. So they can be also viewed as two probability distributions. Okay, and so when we minimize the total cost or distance, then this distance is called the Wasserstein distance. So basically, Wasserstein distance can be used to measure the distance between two probability distributions. Okay, so the optimal transport problem and the Wasserstein distance is closely related to each other. Okay, so now let me talk about the most important application of this optimal transport problem. So this is called the generative adversarial network. So the Gamm problem. Basically, in the Gamm model, we want to train a generative model using the sampled data. And this problem can be modeled as a two-player game. So basically, there is a generator denoted by G and a discriminator denoted by D. And the generator tries to generate data to trick the discriminator. And the discriminator tries to differentiate the generated data from the real data. Okay. So in the most original formulation of the Gamm problem, this problem can be formulated as a minimax problem. So this is a two-player game. Okay. And people showed that this minimax problem is actually equivalent to minimizing the so-called Jensen-Shannon distance between the two probability distributions. So here we use a PR to denote the probability density function of the real data. And we use a PG to denote the probability density function of the generated data. Okay, so the traditional Gamm problem is equivalent to this minimization problem. Okay. And later, people proposed to replace this Jensen-Shannon distance by the Wasserstein distance. So here we use the Wasserstein distance to measure the distance between these two probability distributions. Okay, and the people found that this Wasserstein Gamm is more stable than the traditional Gamm, among some other advantages. Okay, so in practice, people usually consider this Kontorovich relaxation of the optimal transport problem. So here, let's consider two discrete probability distributions. So these two discrete probability distributions are denoted by mu and nu. So for mu, the supports are xi with probability ai. For nu, the supports are yj with probability bj. Okay. So basically, we want to move those red points to the blue points. Okay, so the red points and the blue points, they are two discrete probability distributions. And for the cost function, this is actually a matrix. So here, the ij's component Cij is defined as this. So basically, this is the square of the Euclidean distance between xi and yj. Okay, so this one denotes the cost when we want to move the sand from xi to yj, right? Then for this discrete probability distribution case, the optimal transport problem can be formulated as an optimization problem in this way. So this is actually a linear programming problem. Okay? So this pi ij here, this is our descent variable, and this one just denotes the mass of the sand that will be transported from xi to yj. Okay, and then this one multiplies the Cij, that's the cost. Then we take the summation for all the ij. This one gives us the total cost. Right? So this is a linear programming problem. However, the optimal transport problem arising from the deep learning applications, they are usually of very large scale. So the traditional LP solvers cannot solve them efficiently. So in the machine learning community, people have already developed some more efficient algorithms. So now let me introduce you the synchronous algorithm. The synchronous algorithm actually considers the entropy regularized optimal transport problem. Okay, so without this part, then this is just the original optimal transport problem. This is a linear programming problem. Okay, this part is called the entropy regularization. So this function h is the entropy function, which is defined in this way. Okay. The advantage of this regularization is that this function is actually strongly convex. So by adding this entropy regularizer, this whole problem becomes a strongly convex problem. Now for this entropy regularized optimal transport problem, we can write down its dual problem. So the dual problem is given here. Okay, so we want to maximize this function for two variables, alpha and beta. So alpha and beta, they are the two variables. They're also the Lagrange multiplers corresponding to these two equality constraints, right? And very importantly, we found that the do problem is actually unconstrained, right? And we have two block variables. So very naturally, we can solve this problem by the alternating maximization algorithm. Okay, so the synchronous algorithm actually implements the alternating maximization algorithm for solving the do problem here, right? So every iteration, we just fix beta and we maximize this function for alpha. We get alpha t plus 1. And then we fix alpha, we maximize this function for beta, and that's how we update beta. And more importantly, it can be shown that these two subproblems, they both admit closed form solutions that can be computed very easily. Okay, so that's why this synchronous algorithm is very popular in the machine learning community for solving this optimal transport problem, because it is scalable, it is very efficient, right? Now let's talk about one potential issue about this optimal transport problem. This issue is called crossover dimensionality. So here we assume that there are two probability distributions, mu and nu, and they are unknown. Okay, we only have some sampled data from these two distributions. So we have x1 up to xn. They are sampled from the distribution mu, and y1 up to yn, they're sampled from nu. Okay, and using those sample data, we can define the empirical probability distributions. We use mu hat n and nu hat n to denote them. And you can see, so these two probability distributions, they are discrete probability distributions, right? So one critical issue that in the people consider in the statistics community is the so-called sample complexity of this procedure. Okay, so basically here, this one denotes the Wasserstein distance between mu and nu. We cannot compute it because we don't know mu and nu, right? But we can compute this one. So this is the Wasserstein distance between the empirical probability distributions. So this is just the LP, right? By solving the LP, we can compute this value, right? So then people are wondering, so what's the error between these two, right? Whether this approximation is good or not. So apparently this error depends on the number of sample data n, right? So if you have lots of sample data, then of course the approximation is better, right? So the error is smaller, right? So people already showed that basically this error can be at the order of n to the -1 over d. Let me just remind you that, so this n is the number of sample data, and d is the dimensionality, okay? So then you can see actually this order is actually very bad, because let's say in the high dimensional case, we have d very large, right? So if d is very large, then if you want this error to be small, then your n should be extremely large. Okay, so this is called the crossover dimensionality. Okay, so there already existed some works trying to mitigate the crossover dimensionality. So for example, this paper by Riemannian et al., they proposed this sliced approximation of the optimal transport problem. The idea is very simple. So they propose to project the sampled data points onto a given line, and then compute the Wasserstein distance between those projected data. Okay, and the advantage of this idea is that the one-dimensional optimal transport problem is very easy to solve. Okay, so it can be computed by just a simple sorting procedure in this amount of time. Okay, then of course in practice we don't know how to choose this line, right? So we don't know which line to project the points onto. So then the authors in this paper, they propose to repeat this procedure over several random lines. And every time you can compute one Wasserstein distance between those projected data, and then you take the average of these Wasserstein distances, and using the average as an approximation to the original Wasserstein distance. Okay, so recently in these two papers, this idea has been generalized. So basically here in these two papers, the authors propose to project the data points onto a k-dimensional subspace. Okay, so instead of projecting the data points onto a given line, they project the data points onto a k-dimensional subspace. And this leads to the new model, which is called the projection robust Wasserstein distance, or equivalently, the projection robust optimal transport problem. All right. Okay. So now let me give you the formulation of the projection robust optimal transports. So this projection robust optimal transports, or equivalently projection robust Wasserstein distance, is given by this optimization problem. Okay. So here, see, we have two probability distributions, mu and nu, and we projected them onto a subspace E. Okay. So this E is a k-dimensional subspace in the d-dimensional Euclidean space. Okay. So here we use this calligraphic GK to denote a Grassmann manifold, okay, which is the set of k-dimensional subspaces in RD. Okay. And here in this part, we compute the Wasserstein distance between those projected data. Okay. Then, of course, in practice, we don't know how to choose this subspace E. Right. So then here we consider a worst case scenario. Okay. So we want to find E such that this Wasserstein distance is maximized, and we call that the projection robust Wasserstein distance. Okay. So in this paper by Niels, Witt, and Riglet, they actually proved that for a particular transportation model, which is called a spiked transportation model, this projection robust Wasserstein distance model can indeed improve the sample complexity from this order to this order. Okay. Now let me just remind you again. So N is the number of sample data, D is the dimensionality, and K is the dimensionality of the subspace. Okay. So K is user defined. So K can be much smaller than D. Okay. So then you can see, right? So if K is very small, then in order to have this error to be small, we don't need N to be very large. Okay. So potentially this can mitigate the curse of dimensionality. Okay. So this projection robust optimal transport problem for the discrete probability distribution case, this projection robust Wasserstein distance can be computed by solving this optimization problem here. So we can see that this is a max mean problem. Okay. This constraint, we have a constraint for the variable U. And what is U? U is also normal basis for the subspace E. Okay. And then if we look at this part, this red part, this part is actually the distance between the projected data. Okay. And then basically this minimization part computes the optimal, computes the Wasserstein distance between the projected data. And we want to maximize over U such that this Wasserstein distance is maximized. Okay. And this is an orthogonality constraint. And in the literature of Riemannian optimization, this is also called the Stiefel manifold. So then we can see that this problem is a max-min problem over a Stiefel manifold constraint. So the Stiefel manifold constraint is a non-convex constraint set. Right? So we can imagine that this is a very challenging problem to solve. So before our work, the only existing work for solving this projection robust optimal transport problem is this the so-called RGS algorithm. This is abbreviated for Riemannian gradient ascent meet synchronous algorithm. Okay, basically they consider to add a entropy regularization to this projection robust optimal transport problem. So this is similar as the synchronous algorithm. Right. Okay. So then let's see. In this part, right, after we add this entropy regularization, then this red part becomes the entropy regularized optimal transport problem. And then in the maximization part, we want to maximize this function f eta of u, okay, over a Stiefel manifold. So by adding this entropy regularization here, we know that this minimization part is a strongly convex problem. So then we know that the optimal objective function f eta of u, this is a smooth function. Okay, so once this function is smooth, we know that for the maximization part, we can very naturally apply the Riemannian gradient ascent algorithm. Okay, so then the idea of this RGS algorithm is actually very simple. Basically, every iteration we just take the remaining gradient ascent to update the UT. So here this grad f eta, this denotes the remaining gradients, and this operator is called the retraction operator. It brings the iterator back to the manifold. Okay, because the manifold is a smooth surface. Okay, so when we take a gradient step, we're outside of the manifold, so we use the retraction operation to bring it back, right? But every time when we compute this remaining gradient of f eta, we need to actually solve this minimization problem exactly. Okay, now how to solve this one exactly? Because this is an entropy regularized optimal transpose problem, we know that we can use the synchronous algorithm to solve it. Okay. All right, so basically every time in every iteration of the RGS algorithm, we need to run the synchronous algorithm until it converges to the optimal solution. Okay. So then you can imagine that this part is still very costly, right? So we need to call an iterative solver, right, to solve this subproblem in every iteration. So what we found is actually one iteration of the synchronous algorithm is good enough. Okay, so remember that the synchronous algorithm is also equivalent to the alternating maximization algorithm. Okay, so we found that actually one iteration of the alternating maximization algorithm is good enough. And that gives our algorithm, so the remaining block coordinate descent method, okay, remaining BCD algorithm. Now let me introduce our remaining BCD algorithm.
I have a question.
Yes, sure.
So, so you mentioned that one of the motivation for the Wasserstein looking at the distance and the optimal transport problem is like for the GANs application, it leads to more robust or more stable solutions, right?
Right.
Do we know that this projection robust Wasserstein the thing, does it also share those properties, or are those like for the GANs?
I think so. Yeah. So this is a new topic. So I think this model has not been applied to solving the Gamm problem, but yeah, people have been trying to compare this model with the original optimal transpose model. And so later I will show some numerical experiment results. So we can actually find that this one is indeed more robust to the noise, and also it can mitigate the crossover dimensionality. So basically, if you want to achieve the same error, then if you apply the projection robust optimal transport model, you need a much less number of sample data.
Okay.
Right.
Thank you.
Sure. Okay. So here we also consider the entropy regularized projection robust optimal transport problem. Okay. So this is a max mean problem, and this part we have an entropy regularizer. Right. So the max part we have a Stifel manifold constraints. Right. Then for this minimization parts, we can actually write down the due problem. Right. So we found that the blue part, the minimization problem, the due problem is given by this blue part, the maximization problem here. So again, the alpha and beta, there's the due variables, and they are actually also the Lagrange multiplus for these two equality constraints. Okay. All right. So this problem and this problem, they are equivalent. But then the good thing for this equivalence formulation is that now we only have a maximization problem, right? So we have a maximization problem with 3 block variables. We have alpha, beta, and u, and there's no max mean anymore. Okay, so then basically it can be expected that this problem is easier to solve. Okay, so for the ease of presentation, we can rewrite this maximization problem as a minimization problem. So we define the function g as the negative of the objective function here, right? So for this function, it has 3 block variables, alpha and beta and u. Alpha and beta, they're unconstrained, and u is subject to a Stifel manifold constraint. So then we know that this kind of problem is very suitable for BCD type of methods. Okay, so then this is our Riemannian BCD algorithm. Every iteration, so we update alpha, beta, and u sequentially. So for alpha and beta, we just minimize this function g by fixing the other two variables. Okay, so here we fix beta and u, we minimize the function for alpha. Then we fix alpha and u, we minimize this function for beta. Okay, and then for the u variable, so it has a Stifel manifold constraint. So for this part, we take a Riemannian gradient descent step, right? And also we notice that in these two steps for alpha and beta, these two subproblems, they're actually the same as the subproblems used in the synchronous algorithm. So again, these two subproblems, they admit closed form solutions that can be computed very easily. Okay, so now let me talk about the convergence of our Riemannian BCD algorithm. So basically, we can show that our Riemannian BCD algorithm can find a epsilon stationary points of the original projection robust optimal transport problem. Okay, so this is not the entropy regularized problem. This is the unregularized, the original problem. Okay. First, let me define our epsilon stationary points. So we call pi hat u hat epsilon 1, epsilon 2 stationary points if these two inequalities are satisfied. Now let me explain these two inequalities. So basically, you see this part, this is about the Riemannian gradients of the function f with respect to u. Okay, so this function is smooth for u. So then this one, basically, it means that for fixed pi hats, this u hat is good because the gradient is small. Okay, and the second inequality, it means that for a fixed u hat, this pi hat is good because this function value is just epsilon 2 away from the optimal value. Right, so then this is our main results. We actually can show that this Riemannian BCD algorithm can return an epsilon 1, epsilon 2 stationary points of the original projection robust optimal transport problem in this many iterations, right? And moreover, we can analyze the per iteration arithmetic operations complexity of this algorithm, which is given here. Then by multiplying this quantity and the number of iterations here, we know the total arithmetic operations complexity for our Riemannian BCD algorithm for obtaining an epsilon 1, epsilon 2 stationary point. Okay, so the expression looks very long, but let me just compare these results with the results of the existing work. So we compare with the complexity results of the RGS algorithm. Okay. So in their paper, they used only one epsilon. So we have epsilon 1 equal to epsilon 2 equal to epsilon. So they can actually show that the RGS algorithm has arithmetic operations complexity in this order. Okay. So if you look at the dependence on epsilon, so this is in the epsilon to the negative 12. Okay. And for our Riemannian BCD algorithm, if we have epsilon 1 equal to epsilon 2 equal to epsilon, then our arithmetic operations complexity results reduces to this order. And this is in the order of epsilon to the negative 3. Okay. So then we think this is a significant improvement, right? So we can conclude that in terms of the complexity bound, so our Riemannian BCD algorithm is much better than the existing RGS algorithm. And by the way, these two algorithms, they found the same epsilon station point. Okay, so now let me show you some numerical results. Okay, and by the way, our codes have been included in this widely used Python optimal transport package. This package is now very popular. It's already received more than 1,300 stars on GitHub. Okay, so the first experiment, we consider some synthetic data. So here we consider a uniform distribution over a hypercube. Okay. And we define the push forward function in this way. So this is a push forward function. So basically, the push forward function tells us how to move the sand, one pair of sand to another pair. Okay, so then in this case, we actually know the optimal transportation plan. So then, of course, we know the bus stand distance. Okay, so this is actually also a standard testing example in the optimal transport literature. So for this kind of example, we know the optimal transportation plan. We know the bus stand distance, so it's easier to compute the error. Okay. All right. So here, these are three graphs. They show the optimal transportation plan. So for example, the first figure here, and by the way, here we want to move those red points to those blue points. Okay, and here we have equal to 100 sample data. So these lines they correspond to the optimal transportation plan. Okay, so this is the original optimal transport problem. And this is the results computed by the projection robust optimal transports and using the RGS algorithm. And this is the results for the projection robust optimal transports computed by our Riemannian BCD algorithm. So we can see that basically these two models, right? So the RGS and the RBCD, these two graphs, they look almost identical. So this makes sense because we're solving the same problem, right? So we're also solving the projection robust bus stand distance problem, and they basically give you the same optimal transportation plan. Right. Okay, so this figure shows that our projection robust optimal transport model can indeed mitigate the curse of dimensionality. Okay, so here, so again, because we know the bus stand distance, right? We know the ground truth optimal transportation plan, so we can compute the error. So the error is given in these curves. So the green one corresponds to the original bus stand distance, and the blue one and the orange one, they are the projection robust bus stand distance computed by these two algorithms. Okay, so again, we found that these two algorithms, they have almost identical performance, but in terms of the error, so they both provide a much smaller error than the original bus stand distance. So the x-axis here actually denotes the number of sample data. Okay, so then we can see that, for example, we have n equal to 500, right, sample data. Then the error given by the projection robust bus stand distance is much smaller than the original bus stand distance. So then, in this sense, right, we can claim that this projection robust bus stand distance model can indeed mitigate the curse of dimensionality, right? So in order to achieve the same error, we don't need a large number of sample data for the projection robust model.
Hey,
yes.
Shiqian, I have a question.
Sure. Yes.
So in your convergence results, you proved convergence to a stationary point, right?
That's right. That's right.
So is there any guarantees that your algorithm is asymptotically consistent or something, that the error goes to zero? Because the stationary point might not be the true minimum. Right?
You're right. Right. So we don't have that kind of results. Yeah. So this problem is non-convex, so we can only show the stationary point convergence. We don't have global convergence or something. But yeah, I think here what happens is for this particular data sets, right, for this particular model, we found that we indeed found a good approximation to the global optimal solution. Yeah.
Okay, thanks.
Sure. Okay, so this part we show some CPU time comparison. So basically, we tested the algorithms for many different optimal transport problems with different n and d. Right, n is the number of sample data, and d is the dimensionality. So for all these cases we tested, we found that our RBCD algorithm is the fastest one. It is faster than the RGS algorithm. And these two algorithms, they're actually both much faster than this Frank-Wolf method. I didn't have time to talk about this Frank-Wolf method. Basically, for this projection robust bus stand distance, right, or projection robust optimal transport problem, there exists convex relaxation, and the Frank-Wolf method was proposed to solve that convex relaxation. And we can see that these two algorithms are much faster than the Frank-Wolf method. Okay, now let me show you some very interesting applications. We tested our algorithm on some real data sets. So the first real data set is about the movie scripts. So here we have a set of 7 movie scripts. Each script is contains a list of words, right? And each word can actually be transformed to a 300-dimensional vector. Okay, so then basically, for those words, right? If they come from the same movie scripts, they can be seen as the sample data from the same probability distribution, right? And then using those sample data, we can compute the distance, right? The Wasserstein distance between those movie scripts or these probability distributions. And this way, we can measure the closeness between the movies, right? We will know so which movies are closer to each other and which ones are faster, right? So further away from each other. Okay. So here we have 7 movies, and these are the number of sample data. Sorry, the sampled words. Okay. So here the movies we have Dunkirk, Gravity, Interstellar, Kill Bill 1. Kill Bill 2, The Martian, and the Titanic. And this is the results that we got. So basically, for each pair of the movie, we can compute their projection robust Wasserstein distance. Okay, and let's see, for example, we look at the first column, right? The first column, we found that the smallest value is this one. So this is the projection robust Wasserstein distance. So that means among all these 6 movies, right? So this movie T is the closest one to movie D, and D is Dunkirk, and T is Titanic. Okay, and this result makes sense, right? Because we know that these 2 movies they are both about ocean, they're both about boats, right? So you can imagine that in their scripts, right? So there are a lot of overlaps in words. Right? So also, for example, let's look at this column. Right? This column corresponds to the Kill Bill 1, and we found that this one is the smallest one. So that means the Kill Bill 2 is the closest movie to Kill Bill 1, and this also makes sense. Okay, so basically, according to those projection robust Wasserstein distances, we can roughly group those 7 movies to 3 groups, and again, those 3 groups they are consistent with our experience. Right. Okay. So this is the second real data set. Here we tested the Unlisted data sets. So the Unlisted data set is a collection of handwritten digits from 0 to 9. So this is a sample data set from the Unlisted data set, right? So we can see that for each digit, we have a bunch of handwritten images, right? So then basically, those images corresponding to the same digits, right? They can be viewed as random sample data from the same probability distribution. And then again, using those sample data, we can compute the distance between the probability distributions. So then we will know, right, in the handwritten digits, right, this data sets, so which numbers are close to each other. Okay, so this is the results. So I use the red one to mark the the smallest value in each column. So I also use the blue one, right, to represent some number which is not the smallest one, but close to the smallest one. Okay. So then let's see. For example, we look at this column corresponding to the digit 1. We found that this number is the smallest one. So this is again the projection robust Wasserstein distance, and this one corresponds to the digit 7. So then we know that okay, so the digit 7 is the closest digit to the digit 1. Okay, and then for example, let's look at one more example. Here in this column corresponding to the digit 4, we found that this number is the smallest one. So this one corresponds to the digit 9. So we know that okay. So when you look at the handwritten images, right? So 4 and 9, they're similar. Okay, so basically here we summarize the results given in this table. So we found that for example for digit 0, it is similar to digits 2 and 6, so they can be easily misrecognized. Okay, in this data set. All right. So I think yeah, I hope I convinced you that this projection robust Bus-Stein distance or this projection robust optimal transport model is indeed very useful. Okay, it can be used to solve these new problems, right? Okay, so now let me talk about a new model for computing the mean of a set of probability distributions, and this new model is called the projection robust Bus-Stein barycenter. And this problem can also be formulated as a max-min problem over the Steffen manifold. It is closely related to the projection robust optimal transport problem, right? Okay, so what is the Bus-Stein barycenter? So basically, I want to ask a question first. So given a set of probability measures, what is their mean? Okay, so if we're given a set of data points, right, we know how to compute the mean, right? But what if our data points, they're actually probability measures, right? So how to compute the mean of the a set of probability measures? Then it turns out that the Bus-Stein barycenter can be used to measure the mean of the probability of a set of probability measures. Okay, and this is very useful, and it can be used in aggregating information from several probability measures for histograms. Let me give you a more concrete example here. So in this figure here, on the ground, right? So we have some sensors. Each sensor, they can collect data from the environment surrounding it. Okay, and those collected data, if they are from the same sensor, they can be viewed as sample data from the same probability distribution. Okay, and then those data they will be sent to this transmission tower. Okay, then for this transmission tower, it will need to aggregate the collected data, right, from different sensors. Then the aggregate data will actually is the mean of these probability distributions. Okay, so then basically for this transmission tower, right, it needs to compute the mean of a set of probability distributions, and then using this probability distribution, right, the mean computed here, it can generate data and send to the users. Right. So on this page, I want to motivate that. Convince you that this Bus-Stein barycenter is actually a good measure for the mean of a set of probability distributions. Okay, so for example, in this part of the slide, so here I have let's see, we have 30 images. On each image, we have 2 ellipses. Okay, and then for example, we want to compute the mean of these images. Okay, of these 30 images, and then if we use the Bus-Stein barycenter, so the Bus-Stein barycenter is given here in this figure, and we can see that this one makes sense because still we can clearly see 2 ellipses. Okay, and if you look at these figures here, so they are the the mean, okay, computed by some other approaches, and we can see that basically we don't see much useful information, right, from those results, right? So basically, the Bus-Stein barycenter is a very good measure for the mean of a set of probability distributions. Okay, so now let me give you the definition of this Bus-Stein barycenter, right? So suppose we're given a set of probability measures, so we have m of them. We have mu1, mu2 up to mu_m. Okay, then we want to find the mean of these m probability distributions, right? Then we use the Bus-Stein barycenter. So the Bus-Stein barycenter is denoted by mu, and it is the optimal solution of this optimization problem. So here, basically, this part, right? This is the Wasserstein distance between mu L and nu. Okay, and then basically here we compute a weighted sum of these Wasserstein distances, and we want to find a nu such that this weighted sum is minimized. Right. Okay. So now, as you can see, right, in this definition of the Wasserstein barycenter, this part we have Wasserstein distance, right? And we know that the Wasserstein distance or the optimal transport, right, they have the curse of dimensionality issue, right? So then in this problem, because we have the Wasserstein distance, then it is very possible that the curse of dimensionality issue is inherited here. All right. So then, very naturally, a question arises here is how can we mitigate the curse of dimensionality? Okay? And then we just adopted the same idea as we dealt with the optimal transport problem. Okay. Then we also consider this projection robust burden of the Wasserstein barycenter model. Okay. And in this model, so basically here, let's see this projection robust Wasserstein barycenter. We just replace this Wasserstein distance by the projection robust Wasserstein distance. Okay, we replace this part by this part. And then basically this problem can be written like this. Here, this is the projection of the probability distributions mu L and nu. We project them onto a subspace EL, and then we compute the Wasserstein distance between those projected data. And then we want to find the EL such that this is maximized. Okay. Then finally, we want to find the barycenter such that this weighted sum is minimized. Okay. So then, as you can see, right, this is actually a very challenging problem because you have an inf here, you have a sup here. You actually have another if here because this is the the Wasserstein distance, right? It corresponds to a linear programming problem, right? So overall, this is if, sup, and if problem, right? So this must be very challenging to solve. So then in practice, we need to consider some relaxations. And here we propose to consider two types of relaxations. Actually, we combine these relaxations together. The first relaxation is for those subspace EL, we consider that they are the same. Okay, we use the same EL. And then we also switch the order of the sup and the first inf. So we switch this sup and this inf. So it is like we're considering some kind of a dual problem of this model. Okay. So then we call this the relaxed projection robust Wasserstein barycenter model. So again, here we consider the case of the discrete probability distributions. So this problem again can be formulated as a max-min problem. Okay, and for the max part, we have a variable u. It is subject to a Stifel manifold constraint, right? So you can see that, right? So this problem is of the same form as the projection robust optimal transport problem. The only difference is this constraint set for pi here. Okay, this is a different convex set. So this set is different from the one used in the optimal transport problem. Okay, otherwise the structure is the same. So then, because it has the same structure, we can also apply our Riemannian BCD algorithm to solve this problem. So again, we consider the entropy regularized problem here. Right? We add this entropy regularization, and then for this minimization part, we look at the dual problem. So the dual problem is given by a maximization problem. Okay, so due to the the time constraint, I will just skip some of the details. Basically, this minimization problem, we write down the dual problem. The dual problem is given by this maximization problem. Okay, so here for the maximization problem, we have two variables. We have a little u and little v. And then if you replace this minimization problem by the equivalent maximization problem here, so again, we obtain a max problem where we only have 3 block variables, right? We have this capital U, we have the little u and the little v. So we no longer have a max-min structure. Okay? So we have a purely maximization problem. So we can expect that this problem is easier to solve than the max-min problem. Okay, so equivalently, we can just rewrite this maximization problem as a minimization problem. So it's easier to talk about the BCD type algorithm. Right? Okay, so this is our Riemannian BCD algorithm. So again, we have 3 block variables, right? For little u and little v, we can do the exact minimization for this function. So for the second one, little v, it has a constraint, but still we can write down a closed form solution for this one. Okay. For the capital U, it is subject to a Stifel manifold constraint. So for this one, we just run a Riemannian gradient descent step. Okay, and similarly, we can also analyze the arithmetic complexity of this algorithm for solving, for obtaining an epsilon station points to the original relaxed projectional bust and barycenter problem. Okay, so now I still have some time, so let me talk about some numerical results. Okay, so the first one here, we want to consider a set of synthetic data. For this synthetic data, we can also compute the the bust and barycenter, so we know the ground truth, so it is easier to do the comparison. Okay. Here we consider a set of normal distributions mu L, right? So they're normal distributions, and the bust and barycenter can be computed in this way. So basically people have already shown that the bust and barycenter is also a normal distribution, and with mean computed in this way, and also with the covariance matrix computed by solving this equation. Okay, and this equation can be solved by using a fixed point iteration. So that's how we compute the ground truth bust and barycenter in this case. Okay, so this is about how we generate the data. So I'll just skip this part. This figure basically it shows that in this in this kind of in this particular example, we have the K star. Sorry, I forgot to mention what the K star is. So K star is the rank of the covariance matrix sigma L. Okay, so your mu L is the normal distribution with the covariance matrix sigma L, and when we generate this matrix, we let the rank be equal to K star. Okay, and we have M of them, so then we know that the barycenter should be in this M times K star dimensional subspace. Okay, and then this is actually confirmed by our numerical experiment here. So we tested, this model, right? So the relaxed projection robust bust and barycenter model, right? So the objective function corresponds to the objective function value, and the x-axis here denotes the dimensionality of the subspace. Okay, so in every case, so we consider different K star, right? We found that when this K is bigger than M times K star, then this objective function value is constant. Okay, so this confirms that for this particular example, the bust and barycenter actually lies in M times K star dimensional subspace. So that's why even for example, when your K is bigger than this, right? So you still have the same result here. Okay, I'll skip some of the details because I really want to talk about one real application here. So for the this bust and barycenter model, okay, we applied that to this problem. This is called the discrete distribution clustering problem. Basically, here we were given a set of probability distributions, and we want to cluster them. Okay, so we know that, for example, if we have a set of data points, right? So how do we cluster them? Then the most popular approach is to apply the kmeans algorithm. Right? And it turns out that this kmeans algorithm can also be used to cluster the discrete probability distributions. And this is studied, for example, in this work. Okay. The basic idea is like this. So the same as using kmeans algorithm to cluster data points, right? When you cluster the probability distributions, every iteration we still have 2 steps, right? So step 1, for each cluster, we need to compute its Wasserstein barycenter. Okay, so originally, if this is data points, right, we need to compute the mean. Okay, but now the data points are their probability distributions. So now, when we want to compute the mean, we compute the Wasserstein barycenter. Okay? And then for step 2, for each of the distribution measure, we assign it to the nearest centroid. Okay, then here we need to compute the distance, right? And this distance, again, this is the Wasserstein distance because we computed the distance between 2 probability distributions. All right. Okay. So then we found that in this, this algorithm, right? So every iteration, they need to compute a Wasserstein barycenter. And since we already showed that our new model, right, this relaxed projection of Wasserstein barycenter is better than the Wasserstein barycenter. So then here we propose to just replace the Wasserstein barycenter here by our model, this relaxed projection of Wasserstein barycenter. And we call our new method projected D2 clustering. D2 means discrete distribution. Okay. And here we tested this new algorithm, right? This new kmeans algorithm on 2 different data sets. So I'll just use this one as an example. Okay, so the blue curve here, this corresponds to the original D2 clustering, where in each iteration, when they compute the mean, they use the Wasserstein barycenter. And the orange one, this corresponds to our projected D2 clustering. So every iteration, when we compute the mean, we use the relaxed projection of Wasserstein barycenter. Okay. The y-axis here denotes actually the clustering quality, and we want this number to be big. So then you can see that clearly our approach is much better than the original algorithm. Okay. All right. So I think yeah, we're right on time. So I'll just give a very brief conclusion of this talk. So here we consider this projection robust optimal transport problem. Okay, the main motivation was to mitigate the crossover dimensionality of the optimal transport problem. And this projection robust optimal transport problem can be formulated as a max-mean problem over a Stifel manifold. And we proposed a Riemannian BCD algorithm for solving this particular problem. And we analyzed the convergence, the iteration complexity, the arithmetic complexity, and so on. And we found that our complexity results is significantly better than the existing method. Okay. And in the last part, we proposed a new model, which is called the projection of Wasserstein barycenter. It can be used to compute the mean of a set of probability distributions. Okay. So the main message I want to deliver from this talk is that the Riemannian optimization is actually a very exciting area. It found many interesting applications, but still, currently it is relatively less developed. So I'm really excited about this area, and I think there are plenty of important questions to consider in this area. Okay, so this is a list of my recent works on Riemannian optimization, and this talk is mainly based on the first 2 papers. Thank you very much for your attention.
Thank you, Professor Ma, for a wonderful talk. We have time for a couple of questions.
Shiqian.
Yes,
So,
yes, Zhao Song. Yeah.
Very nice talk. I truly enjoyed. So I wonder how eta, the parameter eta for the regularization, you have the parameter, right? How eta affects the quality of solution and also the speed of the algorithm?
Of course. Yeah, very good question. So I think, yeah, you know the synchronous algorithm, right? So the synchronous algorithm, I think, has the same issue here. Basically, yeah, this eta, right? Let me go back to the slides so we can, yeah, look at this one together. So, yeah, okay. Basically, yeah, let's see this this eta here, right? So in the entropy regularized optimal transport problem. So of course, this is regularization, right? So we want eta to be small, right? So for small eta, then this problem is closer to the original problem, right? But if the eta is too small, then numerically this is not very stable. Okay? So I think yeah, this has been also observed, in the machine learning community. So I think in practice, what they usually do is to choose a eta which is not very big, and not very small, right? They need something in the middle. Yeah. So for our work, so for this projection robust optimal transpose, we also have this kind of issue, and we do not have a very good way to systematically choose eta. Basically, we just tune a few choices of eta for the particular application, see which one works the best.
Okay, thank you.
Yeah. Mm-hmm.
So also very quick, sorry. So when you do this, so how many remaining grading steps do you take in this synchronous approach when you basically do the alpha, the beta, and then do the grading projection, right?
That's right. That's right.
How many steps do you do? So is it all like one step, or do you gonna do more?
One step. You mean the BCD part, right?
Yeah. Yes, the BCD.
Yeah, in the BCD parts, yeah, it's like, yeah. So we just let's see, these two exact minimizations, right?
Yes.
They have closed form solutions.
Right.
Right. So they have closed form solutions. So we just compute them by applying the closed form solution formula. So yeah, we just one step of alpha, then one step of beta, then one step of U.
Yeah, but why not our why not more steps?
Right. So if we do more steps of alpha and beta, right? So that's actually is this algorithm by Tianyi Lin. They have this RGS algorithm. I think that's what they do. So basically every iteration. So before you update your U, right, you apply the synchronous algorithm to solve this red parts, and then you run a few iterations, right? Then you stop. Then you update U. Right.
Yeah, but so, you may also take more steps of the grading steps over the manifold.
Of course, yeah, I think you're right. Actually, if we look at the CPU time comparison, actually our advantage is not very obvious. Actually, so to be honest, right. So if you look at, for example, those numbers, right, they're seconds, right, and comparing with this one, right. So for example, this one, right, they're pretty close. I think the reason is that the synchronous algorithm is already very mature, so people have very good implementations for the synchronous algorithm solver, and they can do parallel computing. And for that part, they're very efficient. So even though, for example, you run like 10 steps or 20 steps, it doesn't affect much. Compared with we only run one iteration. Right? Because I think the bottleneck is when we run the Riemannian gradient step.
Yeah.
That part, right? You have you have the retraction operation, right? You need to compute the gradients. So that part, I think that's the most expensive part. Right.
Yeah, but then okay. Related to that, have you also tried to use the cubic regularized? I think your objective function is very smooth.
Yeah, that's nice, right. That's right. Yeah. We didn't, but I think that's definitely a good idea. So right for this, let's see where's the algorithm. Yeah. So for this, right, for the gradient, right? So for the Riemannian gradient step, so you can try second order method or even like a cubic method.
Because then I think it's going to be a lot more expensive. It's similar, comparable.
That's right. That's right. Yes. Yeah, I think that's definitely a good idea. And we haven't thought about that yet, but I think it's definitely a very good idea to analyze the complexity and also see whether it improves the results or not in practice.
So maybe this is a good place to end the official part of the talk. We do have a reception for anyone who wants to stay back.